All right, we are going to finish the topic of heat engines today and go over the topic of entropy. For anybody watching this potentially in the future, I did just show a couple of videos on YouTube. One is What is Random by Vsauce, and the other is What is Not Random by Veritasium. All right, let's go here. Like I said, I do need to finish heat engines. When we last left our intrepid heroes, they were discussing the second law of thermodynamics. What is the second law of thermodynamics? We haven't got there yet in the topics. No. What is the second law of thermodynamics that as we stated it on Friday? Yes. Correct. Energy cannot be efficient. Colloquially, the standard way of saying is the first law of thermodynamics says energy cannot be created or destroyed. The first law of thermodynamics is the conservation of energy. The second law of thermodynamics is, yeah, even though it can't be created or destroyed, you're 100% of what you put in is almost according to the law, is never going to be 100% of what you put out, right? Another way to say it is the first law is the best you can do is break even. The second law is I can't break even. I can't even break even in this particular process. So what we said the other day is that the heat energy coming into a system, okay, basically of all the heat energy that comes in, if I put 100 joules of energy into this system, what this states here is can all 100 joules be used by the system? No. So in other words, this is automatic. This fraction right here is automatically going to be less than 1. What we're going to talk a little bit about today at the end of this particular section, because we're not quite done with heat engines, is the most efficient possible heat engine that has even come up. We haven't created it, but conceptually. Now, to very, very quickly go over this, because there's a lot of stuff here that I want to make sure that you have, like, okay, what should I have gotten from this? Okay, things that you should have gotten from this particular process is why does a heat engine go clockwise, and why does a heat pump or a cooling why does it go counterclockwise? That, of course, has to do with the PV graph and talking about those signs on positive work. As I come up here, is that positive or negative work on the gas? Negative work on the gas, right? And positive work on the environment. And then if you flip back down going this way, of course, that is positive work on the gas or negative work on the environment. So this is an engine because it's doing work to the environment, right? It's losing energy in itself, it's gaining energy elsewhere. Does that make sense? And the reason, of course, why that works goes to my second point in just a second, and that is simply the amount of work that is negative is greater than the amount of work that is positive on the gas, and thus it loses the total amount of energy, and that's because it's spending it elsewhere. Yes? Where if I put the arrows the opposite way, the opposite is true, and so it gains energy or takes energy away from the environment, aka that is a cooling engine. Bringing me to my second point for the other day, and that is that the area inside here is the amount of work that is being done. And if you struggle with that idea, let's just give a brief example up on the, I should probably do it on the screen since we're recording. Come on, that's good. Here we are. For example, if I made a system that looked like this, and I went here, 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 and this is 1, and this is 3 times 10 to the 5th pascals. Okay. And this is 1 meter cubed, and this is 3 meters cubed. And of course, I ask you to find the work done by this process. That's just area under the curve. That's what you always know, right? And how would you calculate the, how much would it be to go from, excuse me, here to here? Why don't you discuss that quickly in your group? How much work is done when in the first process as it goes from the first state A to the second state of B? Discuss how much energy is done there. Go. do math. I mean, I know it's Monday. We got this. I know it's raining outside. You can do this. I believe in you.
Well, 2 times 2 is 4, right?
Look at you go. You're already there, halfway there.
2 and then 2, it's 4.
It's 4. It is 4. Correct. By the way, just if you haven't noticed this already, they try to be nice to you when choosing these particular units because they're regularly doing 1 times 10 to the 5th up here, right? Or in other words, 100,000 pascals and regularly multiplying by 1 meter cubed. So of course that means the energy that is being used is 100,000 joules. Yes, just pressure times volume in that case. If they ever use ATM and liters, okay, I would highly suggest you do that conversion because there's a really nice conversion within there to be able to use. We'll talk about that if we have a little more time today. But in other words, this is 2 up here, right? 2 times 10 to the 5th joules, and this is 2 times 10 to the 5th joules here. Should it be positive or negative? It is one of those. It is positive or negative. It is negative, correct. So it's negative 2 times 10 to the 5th joules minus 2 times 10 to the 5th joules. And as I step from B to C on process 2, how much work is done? Absolutely none because the volume hasn't changed. And if I step from C back to A on process 3, how much work is done? What's that? 2 and positive and negative? And the reason I wrote it this way to begin with on process number 1, 2 is 0, and 3 is, like I said, positive 2 times 10 to the 5th joules, of course canceling out that much that was added earlier. Thus, this is just area inside the curve. Does that make sense-ish? Cool beans. All right, slideshow from current slide. Come on, do the thing. Do the thing. I got too much stuff to do to worry about you right now. Come on. Why are you being difficult? Why you hurt me so? Okay. Let's try again.
Oh, it's over.
It's over. Oh, I know what it was. It was because it was
It's over. Is it crazy? It's over. They're all white slides. Oh no. Oh no. No. How are we ever gonna lay out people?
While your jokes are absolutely hilarious,
Oh, no,
nobody can deny that. We are testing Friday come hell or high water. I think you're going to want this.
Testing Friday?
I thought we were doing Thursday.
Oh, Lillian's so happy.
I thought we were
You
testing
I moved it back a bit.
I thought you moved the notes. Actually changed because I thought it was.
I had actually
before.
changed it.
Oh.
I thought you just meant you're moving the notes back a day.
No.
And we were slowing down Thursday.
No, you're going to want 2 days for it. All right. So, too much to do. All right. So we had this conversation before. If you've not yet already like kind of gone through the reading and done it yourself, until you do that, good luck, right? Once you do that, obviously we can have kind of similar conversations about like how this works. But it takes me a while to kind of go over these as I'm thinking about them as well. So we have energy come in from a heat reservoir, goes into the heat, engine is used, and heat comes out. And like I said, essentially for a perfect, efficient system to happen, boom, that could not occur, right? And the issue there, of course, is if that doesn't occur, the only way that doesn't occur is if the engine is at the exact same temperature as the environment, right? But of course, if the engine is at the exact same temperature as the environment, did this occur to begin with? No. So we've got a situation here potentially. All right. So we talked about this the other day. Essentially, if I've got, I think I said if 100 joules come in here, right, and I'm going to change the number slightly, and 80 joules leave, that's because, of course, 20 joules was done on the environment, or negative 20 work happened in that particular case. And then efficiency is defined as how much work is done by the engine compared to how much energy originally went in. And then we got to this guy, well, work of engine is just the difference between how, like the 100 and the 80, right? How much I put in versus how much came out. And so from that, we rearranged it into efficiency as 1 minus QH over QC. Okay? In my numbers I just said a second ago, I said 80 joules came out, 100 joules went in, which would make that 0.8, or 1 minus that means this is 0.2. That particular engine would be running 20% efficient. 20% of what we put in is actually coming out. Everybody good there? Cool beans. All right, so then we ended talking about, this slide is kind of a little bit different. These are ways to show how good something is at cooling or good at something is at heating. These are not as much physics equations as they are engineering equations or HVAC equations to be like, hey, how good is my refrigerator? How good is my heater? That type of thing. All right, so the second law of thermodynamics, like we said, first law says we can't get a greater amount of energy than we put in. Second law says we can't even break even. We can't put all the energy into a system we want. Here's the easy way to see thermodynamics in an example we gave last year. Spainhour starts a roller coaster on this hill. Why can't you have a second hill that is higher than the first? Because you would need more energy to put in. So if you started at rest up here at 100 joules, the best you could possibly do is get to 100 joules. That being said, you all know that's not even realistic. If you had a roller coaster of the same two hills, would it be a very good roller coaster? No, because some process is removing some of that energy. What process is removing that energy? Friction. Friction's taking and doing work out of it. Thus, all the energy I put in, the best I can do is maybe 70% of that actually goes to what it was that I was trying to get out in that particular time. That's thermodynamics in a nutshell. Now, reversible and irreversible processes. What I'm about to describe to you is a very, very specific situation, and I kind of want to blow through it really quick because A, you can do the reading, and C, the example itself is not quite as important as the result. A reversible and irreversible process is meant to essentially say, hey, well, exactly what it says. I can do it, I can take it away, and I'll get the exact same outcome. So imagine, if you will, right here, we have a energy reservoir on the bottom, and we have a piston, and we are very, very, very slowly changing this piston by placing grains of sand onto things, and of course increasing the, what would putting grains of sand onto a piston increase? To one step back, but yeah, eventually you're right. It's going to increase the gravity, right? The gravity weighing on it would be basically the force of gravity caused by these grains of sand plus the atmospheric pressure from the outside. So yes, in turn, you would be correct. It would be increasing the pressure on the inside. We're discussing what's known as the Carnot engine. Carnot because it's French. All right, so there's 4 processes by which you pull off the Carnot engine. In the first process, you have a hot reservoir from the bottom and allows it to expand isothermally. How is it expanding isothermally? Well, if it expands, right? If it expands, what should happen to the temperature? It should go down, right? So we are expanding it isothermally because we have the heat reservoir underneath, right? So as it goes up, and the way we would have it go up is slowly remove grains of sand to let it go up, but we're putting in energy at the time to make sure it stays isothermal. Okay, you can see that with the ridiculous, meticulous nature that you would have to have in order to pull this off is very unrealistic. Okay, next. So there we go. So we have the isothermally in this process. Next, okay, let the gas expand adiabatically. See, now it's at a higher temp. It's still at that higher temperature, right? We've kept it the same, but now it's got a little bit more energy to push because it's a little bit hotter, right? So because it's hotter, it's still going to push a little bit more. It's going to go out a little bit further. But adiabatically means now you'll notice there's thermal insulation. There is no heat coming in. That's what makes it adiabatic. And so what should we expect to happen to the temperature? It should decrease at this particular time, 100%. Okay, next, from C to D, we basically do the exact same 2 opposite processes. Now we put a cold reservoir underneath there, and it will compress. And normally, if it compresses, we would expect temperature to go up, which is why we have a cold reservoir to take that energy out, so it stays at the exact same temperature. And once again, it's going to continue to go adiabatic. It's going to be 2 temperature. It's going to go even lower in this process. To show that on a P versus V graph, here it is. The first graph was Q to be along an isotherm of this hot temperature right here, and Q is coming in. Yes? Notice no Q whatsoever is coming along this process because this is the adiabatic. Notice it is still expanding because volume is getting bigger, but notice that its temperature is dropping as it goes from this isotherm down to this one. And then C to D should be the exact opposite. Isaiah, you with me, buddy? I know it's not easy to stay with me right now, but here we go. Okay, from C to D, we take energy out so that we can compress it, and then it's going to compress even further, raising its temperature very quickly. This is known as the Carnot cycle, a specific combination of isothermal adiabatic, isothermal adiabatic. So Carnot is those two specific processes. There may or may not be a reason I'm saying that, but you do what you want with that information. Okay, now here's the deal about a Carnot engine and why it's specifically important. The temperature, the QC, as we well know from the previous section, is specifically related to that temperature, right? The temperature is remaining constant while I'm putting energy in, yes? The temperature is remaining constant while I put energy out. So the relationship, okay, the relationship between how much heat goes in and how much heat goes out is directly related to what temperature those take place at. Yes? Now, the equation, if you remember previously, for efficiency was this guy right here. So this should all be review of a previous slide. Let me finish my thought, Trent, and then I'm with you. Okay, so efficiency is how much work the engine is doing, how much energy I put in. And as we already said today, we reviewed, the work of the engine is just the difference between how much I put in and how much comes out. Yes? And so I rearrange it to this. But as we saw right up here, these are directly proportional, the ratio of these heats. On a Carnot engine only, let me be very clear here, this only really works for a Carnot engine, are directly related to their temperatures. So I can replace this ratio over here with this ratio over here. Yes? The Carnot engine is known as the most possibly efficient engine, and it is entirely theoretical. Carnot theoretically made this. He did not actually make this. Okay? So what we get out of this is, simply put, what would have to take place in order to get, let's say, I don't know, 100% efficiency. Well, this is what we talked about the other day, actually. What would have to take place such that this is a perfectly efficient engine? Temperature cold has to be 0. And if you had to guess, since we're dealing with ratios here, is that on the absolute scale or any other scale? That's absolute. Those are in Kelvin, which means that has to run at absolute 0 in order to be perfectly efficient. Now, in truth, obviously, what's the cold temperature? And for like a Carnot engine, well, if we're here on Earth, probably whatever the temperature of the atmosphere is. So let's pick I don't know. Let's pick 25 degrees Celsius. Okay? Now, this means I get more efficient, weirdly, if the temperature coming in is what? Hotter. The greater difference between the two, the better I can get. So let's say that temperature inside is, I don't know, roughly, I'll go hotter than boiling water. Let's go 150. Okay? So here's your two numbers again. Atmospheric is 25 degrees Celsius. And I'm saying the engine's running at about 150 degrees Celsius. Please calculate for me, what is the efficiency of that engine? Atmospheric is 25 degrees Celsius. Careful with what I said earlier. What should those units be in? So you have a Carnot engine, which is the most possibly efficient engine, by the way. No actual engine runs nearly this close to efficient. And I just told you that the heat of the engine is running at 150 degrees Celsius, and the cold is just atmospheric. What is the efficiency of said engine?
29.
Yeah, about 29, 30%. If you're not getting that, you're not in Kelvin probably, so make sure you go to 25 plus 273, of course, to get to Kelvin, and the 150 plus 273 to get that. Questions? Yes?
Why can't it be T over TH?
Because they're directly related. What do you mean?
Here,
heat would equal work for isothermal, right?
For isothermal,
Heat equals work.
yep. Correct.
Work equals the whole nRT ln of volume.
Let's go back to Q. How do you get Q?
Reservoir.
From a heat reservoir, from power, right? So you have This is changing? No? Well, so it's some number but not affecting it. Okay? Is this changing? No, not affecting it. Is this changing? So what is it? What is Q directly related on? What's that? Whatever. In this particular case, it's whatever the temperature of the gas is.
But it's still gonna, wouldn't the difference still be almost? Because you keep it at,
No, careful here. TH is the heat reservoir on the outside. So it would be hotter than the gas. And the gas is staying at the same temperature, T, because it's isothermal.
I thought we're trying to keep the gas at TH. And then remove sand so it gets a little colder.
I think we're getting, you're right. You're absolutely right. So it is technically the TH would arguably be the second one, and TH up there is actually something hotter, but it still remains the same that whatever that hot temperature is, forget the specifics. You know, I don't care which one you're talking about. Are these both constant? Yes. And are they directly related to this Q that's going in right now? Yes. Now, what about the time? What do you do? Well, if you're in the reading, what it says is we actually, and again, getting very meticulous here, we attempt to form this reaction so quickly that time is a moot point on this particular front as well, which is going to be really hard to do with grains of sand. But keep in mind, grains of rice, but it is 100% theoretical. It is not an actual thing that they are attempting to actually pull off quickly moving rice here and there off the thing. And also, you're kind of missing the point of what it's attempting to get to. All right. All Carnot engines operate reversibly between the two temperatures, thus have the exact same efficiency. All right. I apologize, I'm cutting this conversation off because I got 30 minutes to discuss entropy. All right, all real engines operate irreversibly due to friction and the brevity of their cycles and are therefore automatically less efficient than the Carnot engine. The Carnot engine, as it says right there, is talking about kind of to be done. I said small time, I think it's a big time. It's done with the big time, and there's arguably absolutely no friction. So since there is friction, and done extraordinarily quickly in these particular cases right here, automatically all engines are less efficient than the theoretically most efficient engine of a Carnot engine. All right, we already kind of did that with an example. Let's freaking talk entropy. What is entropy in a nutshell? Well, ultimately this measure is, this is a measurement of disorder. This is a measurement of the usability of energy. Okay? If I open this deck of cards, which has been played with a bunch, this is a crazy thought as we're getting into a little bit of statistics here. Okay? Do you know what the likelihood is that this is in the same order, the exact same order that it was when it was first given to me?
Not very likely.
What's that?
Not very likely.
Basically, it's 52 to the exponent. Okay? If you want to do the math on that, the likelihood of this being the case is so little. If I put a different orientation in this every single second that the universe has been alive, it would still be beyond possible that it has ever been replicated. Another way to put that more colloquially is you can say that if this has been shuffled, if that's been shuffled properly, no, that order has never existed before, nor will ever exist again. And that's weird to think of, because there's only 52 cards specifically in that deck. And to think that this deck's order right now is unique amongst all orders that have ever been made of that deck. Does anybody know roughly, if you, I don't know, you're gamers or anything, what is the number of times that you're supposed to shuffle before you have the most possible randomness? 7 times. You can do 8, you can do 9, obviously you'll get slightly more random, but you get diminishing returns. After 7, you can pretty much be certain that that is utterly and completely random. Or, again, that order has never been replicated by any deck from the beginning of the universe until now. It's insane to think that it does in fact have that level of uniqueness, but it does. And if you don't believe me, then sometime today, put 52 exponent on your calculator and see how many possible different ways there are. And then when you think about the time of the universe, imagine actually choosing a different orientation every single second if you could somehow pull that off, and it would still be completely unlikely that this has ever existed prior or before that. What's up?
Just to clarify, 52 exponent is the same thing as 52 factorial, right?
Yes, 52 factorial, correct. So, what do I mean by this? Well, when this was given to me, this was given in a very specific order, okay? If anything happens to these cards whatsoever, would you expect the cards to become more ordered or less ordered? Less ordered. That's entropy in a nutshell, right? If you pass by a room and there is a deck of cards, I'm sorry, a house of cards, meaning somebody has meticulously placed the cards such that they are up and structured in a very organized way, what is your first thought? Is your first thought, man, somebody must have done that? Or is your first thought, they got lucky that the cards happened to fall that way? I'm going to go ahead and guess it was the first one and not the second one. And quite frankly, gravity itself would tell you that where should the cards go if there is kind of a jostling of their particular order. All the way kind of to a pile on the ground, kind of much more random than what it is in this particular case. Entropy basically says this, okay? I can use energy, and I'm going to take energy from an ordered state to a disordered state. I am going to use that energy. I could get it back more ordered, but I'm going to always increase entropy. Meaning, I got you here, okay? Let's imagine if you will, we put a gigantic rock on top of the hill, okay? Such that it has 100 joules of energy. Give it a push. That energy comes out, yes? Now, can I order that energy again in the exact same way as it previously was? Meaning, could I put the rock right back where I found it? Yes, 100% I could. But how would I do that? What would I have to do in order to give 100 joules back to this rock?
You have to create disorder in the environment.
Close. Not quite what I'm looking for. You have to put energy into it. How much? Would you have to put 100 joules in? You have to put more. You're not efficient, correct. As a matter of fact, we said human beings are some of the most efficient engines there are. You run at 25% efficiency, which means to return the 100 joules to the top of the hill, you've got to spend about 400 joules, roughly speaking, to pull it off, right? So what happened to the total entropy in the system? I was able to locally increase, to decrease entropy. I brought order. I brought order to it. I returned order to the system. Except in the process of returning order to that system, what happened to my system? It got more disordered in that particular point in time. So, entropy of a system always increases. Disorder always increases. The randomness of energy usable in the universe always increases. This brings about the idea that you potentially heard before, that we will eventually, the universe has a heat death. Have you ever heard the heat death of the universe at all idea before? Okay, the idea is that there's a bunch of energy in our universe, but at some point in time it will be unusable. It will be so random, so disordered. Essentially, our universe will be, back to the video we talked about earlier, that what am I trying to say? The white fuzzies that you saw across the video. The entire disorder of energy in the system will increase to maximum information, maximum amount of entropy, but we can't use any of that. Now, great news for you is that we, and also when I say we, I'm not just talking about us in this class, probably humankind, will have long ceased to exist before that has ever come into existence. Now, I don't know that for sure. I'm not in the future, but I think if I could be logical about the path of like all species thus far that we have seen, I think it's very reasonable that we human beings will not be around ever to see that. And if you are, congrats. All right, please feel free to throw one up at me at that point in time when you are at the heat death of our universe. Like, ha! Spainhour, I think that was his name, was a minute ago. You were wrong. I made it. Congrats, I guess, but you're probably alone. All right, moving on. So, what does this say? The change in entropy is defined as this. It is defined as QR, the energy going into the system, divided by the relative temperature that it's at. So, for example, hold on, I'll do that in just a second. Entropy of the universe increases in all natural processes. Is there a process by which that you believe strongly that I could drop 52 cards every second now until I pass, or let's say like I put someone in my stead, so now until the end of time we'll just have somebody always taking 52 cards and dropping them, and House of Cards. Well, not that one. 0 out of 1. Do you think that that would ever happen, that they could hit? Now, is there a possible way? Yes. Is there a possible sort of system that it could? Yeah, I mean, there is. How awesome is that? I'm sorry, there's a couple jokers in here. 54, my bad, I didn't mislead you. I'll pick up the cards later. When I say that, and then I'm finishing picking up the cards.
One of the issues when you're doing.
Ooh, look at what I'm doing, guys. I am I've decreased entropy just now. How did I decrease entropy? No. Decreasing entropy means I put more order into the system. What did I do? You just watched me do it.
You increased your order.
Interestingly enough, when you start to think about like human beings as a whole, specifically unstructured human beings, let's call them children. Okay, I'm dealing with this a lot at home right now, but I think it's an important actual lesson here. Do human beings naturally crave entropy, or an increase or decrease in entropy? Naturally. Say naturally, we increase entropy. When you look at small children, okay, and the way they play with their toys, okay, I think it would be uncommon for you to like be watching a small child, and then if that small child, when it's done playing with toys, okay, it's nap time, gets up and goes, well, I do need to make sure this is well ordered for the next time that I play with these toys. So I'm going to get all of these blocks and organize them over here and put the magazines back where they go and take these dolls and put them in this particular corner. And my Legos, those don't need to go on the floor. So I'll put them in a very structured way in this bag. That seems a little bit uncommon. And if it is common, you would probably think to yourself, that child has been taught that particular skill to decrease entropy in that particular. Now, what's really fascinating, okay, now I'm going to take a small break and mention this, and I know it's on video and it's completely fine. There is parts of this particular conversation where personal beliefs that I hold might somehow accidentally bleed into this particular topic. And you might see in some of your cases where it is. Please understand that I'm doing my absolute best to mention the facts that we are seeing up here and just point out kind of conclusions out in the universe, and I am not attempting to assuage you or to make you believe anything different than what it is. Life itself, increase or decrease in entropy? Disagree strongly. Life itself is very much a, you said increase, right? Is very much a decrease in entropy. Is life itself ordered or not ordered? Let me give you a hint going back through some of your classes. What is the, do you guys potentially have a blueprint? You have DNA. Why do you have, and how does that DNA work? Well, it's in a very specific order in order to produce you as you are. So even if you want to go down as simply to the idea of molecules and DNA itself is extraordinarily ordered. Now, to make sure to bring counterpoint to my particular issue, I've already said this, it is entirely possible to bring about order over here as long as over here we decrease order even more. Okay? So physicists would say, okay, and biologists would say along this lines, yes, we know that life itself is in fact a decrease in entropy. This is not up for debate. I don't want you to think that that's a personal belief. That is, life is definitely a very strong decrease in entropy. You are very much ordered, and quite frankly, the moment you spring into life, you are decaying due to entropy, right? The inception of you to become alive was the most ordered to happen, and now why do human beings die? Well, our organs get worse. Our organs get worse at repairing, and we fall into entropy over time, and eventually we all die, whether it be let's say natural causes more than the others. Natural causes would be to an increase in entropy within our bodies. We are subject to entropy over that time. If we were not, well, then we would pretty much all look like where we were when we maxed out on our, for some females, usually 18, 19. When you go to full maturity, if you didn't have to deal with, if human beings didn't have to deal with entropy, we wouldn't have wrinkles, we wouldn't have organs failing us, we wouldn't have that thing. We would just, they would exist just the same as they always do. But so entropy of a universe increases, and all disorder in the universe always increases. This number always goes up. One of the easy math ways to see that is simply this. I have a batch of cold water here. Cold water at a colder temperature. Yes? I have a batch of hot water at a hotter temperature. What do you expect to happen to the temperature as they combine together? It would even out. Correct. Now, what would you expect to happen to heat over here? Heat would leave, and of course over here it's... So what is true of the Q hot energy leaving here and the Q cold energy coming in here? They're of course equal, yes? So the Q hot and the Q cold in magnitude, I'm not worried about sign right now, are completely equal. When you look at that equation right there, Q hot, Q cold, do they actually have the same entropy? Do they both change entropy the same amount? Let's actually put the signs back in it now. Which one of those is weirdly gaining order? Which one of those is reducing? And I notice I've taken off the absolute values now. Which one is gaining order? The hot. Slowing down. It's becoming more ordered. Kind of moving towards solids is a way kind of things are. When you think about gas, liquid, and solid, which one is the most ordered? Solid. They're the most ordered. That would be the way potentially to go. So this is definitely losing. It's losing entropy, right? We're decreasing entropy. We're ordering the hot, except T hot is the same, and T cold is the same. So, well, T hot is actually negative. Okay, so some negative. I'm going to make up a number real quick. Let's say 10 joules. Okay, and that's positive 10 joules. Except here's the thing: based on the word hot and cold, what's automatically true of this number? Larger than the other. So if I say this is, just for the sake of simplicity, I know 10 degrees Kelvin is ridiculous. Okay? And this is 5 degrees Kelvin. Then yes, entropy in here has decreased by 1 joule per Kelvin. But over here, entropy has increased. So the total system, this one, gained order. But this one got more disordered in that particular process. All right. Which of the following is true for entropy change of a system which goes through a reversible adiabatic process? Reversible, of course, meaning that adiabatic meaning, of course, I could put up here, we go, I got you. Reversible adiabatic process. This is pretty darn close in this particular case. Reversible adiabatic. Here's adiabatic. What does adiabatic mean? Remind me? No Q, okay? And here, for the most part, it's reversible. I did it quick enough that Q really shouldn't have had that big of an impact. Now, in the first process, what happened to its temperature? Goes up, but then it goes back to room temperature. So what should it be in this particular process? Actually, don't even think about the temperature. I said something else here a second ago that should actually tell you what this is. It should be zero. Why should it be zero? There's no Q. We said it a second ago. By definition, there's no Q, there's no change in energy, and so there is no impact on that whatsoever. Entropy and disorder, as I said already. Disordered arrangement is much more probable. That's the other way to think about entropy. It is a measure of what is the most probable. Is order the most probable? Well, do you know how many possible options there are of a this is a royal flush right here, of a royal flush in a deck of 52 cards? How many possible options are there? Four. There's four. Do you know how many possible options there are of combinations of 5 cards? It's a few more than 4. Okay? We're up in a very, very large number. So, inherently, which is more likely? Order or disorder? Disorder. 100%. Okay? Again, like I said, isolated systems tend towards greater disorder. Entropy is a measure of that particular disorder. This equation right here, it's a statistical one. We see Boltzmann's constant right here, which, interestingly enough, is joules per Kelvin. And what did I say the units on disorder are going to be? Joules per Kelvin, based on that guy right there. Oh, reminder of this last equation, by the way. Please notice that this is change in, right? That is not disorder. That is change in disorder is defined that particular way. Boltzmann's equation was the relationship between R and the number, Avogadro's number. Yeah. Yes? Okay.
Whatever has like order or disorder is defined by us, right? Like for the cards, both cases are equally probable. We're just choosing that.
Well, order defines, I mean, I hear where you're at, but I'm going to say no. I'm going to say that order is, let's say we had never found out DNA sequences. You guys know that there's 4 letters in a DNA sequence, right? It's AT, it's GC, unless you're going for RNA and that switch happens. Is it AT, right? Yeah, it's AT. I mean, you're mean replaces T, isn't it? Yeah. Yeah. We never found out if human beings never identified and lettered them, right? And by the by, you should keep in mind that lettering is 100% obviously English related. It's different, of course, in other languages and that way. But would that order have still had to exist in order to create life? If you define, I'm going to say no, or whatever we are defining as order is the thing that naturally decreases. Okay, you don't want to call it order. I don't think that somebody else could come along and say, see, we have created a system. We've created these numbers. Thank you, 2, 3, 4, 5, all the way to 10, then Jack, then King, then Queen. I said Queen, then King, right? That is the order that they go in. That is the one order that they specifically go in. So, if we had made a different order that they go in, it'd still work out the exact same way, right? If, for whatever reason, if we said it goes 2, and then it goes 7, and then it goes 4, and then it goes Jack, and then it goes Ace, that's a royal flush. There'd still only be 4 possible of those options in a deck of cards, and there'd still be just as many options for what isn't that in the deck of cards. So inherently, this particular process of order is, again, less likely. All right, so this equation right here is it's not perfect. W is not work. W is the likelihood of an event to occur. It's messy, but essentially here it is in a nutshell, okay? If I draw 4 random marbles from a bag, and that bag begins specifically with 20 red marbles and 20 green marbles, and they are purposefully replaced, okay? If you've been in statistics, you've definitely heard these conversations before. But how many possible likelihoods are there of pulling all red, okay? 1. One possible option. In this particular case, by the way, the setup here, W would be 1/2, right? Why 1/2? Because W is the likelihood that I would grab a red or green marble, and if I have 20 and 20, completely replacing them, it would always be 1/2, would be assuming that it's entirely random that I'm pulling them out. Okay, so how many possible options are there for straight red? Just 1. How many options are there for 1 green and 3 red? 4. Right? I could pull the green, I could put the green last, third, second, or first. And then all of the rest of them have to be red. Then I finally get into what about 2 green, 2 red. There's actually 6 possible options. I'm not going to read them off. 2 and 4, and then 1. And then obviously there's statistical ways of calculating this. So which of these systems would you say probably has the most order?
2 green, 2 red.
I would say all red and all green. Has the most order to it. Is that more or less likely? That is the least likely. That is 2 out of 16. There are 14 other options which have more disorder than those 2. Now I see what you're coming from with the 2 and the 2, but here's another way to put that. Disorder kind of by nature is like the randomness. It's all over the place. Which one of these has the most randomness and the most possibility or the most, that's the other thing. By definition, more random really has more possibilities, right? Because when you think about what randomness is, all the possible orders, randomness is the likelihood that they're going to be kind of all over the place. Yes? Okay, yes.
So obviously I know how it would affect it from like a math point of view, but what if you just don't put the marbles back in the bag after you draw one?
It's just, I mean, it's still going to be, still going to change the statistical values, and the reason why we put them back is so that I can just say 1/2 as opposed to talking about how that percentage potentially changes over the course of the action. But still, entropy, you can do the math on all of these. Okay, as a matter of fact, if you go to a thermodynamics class, pretty much every unit that we have in Physics 2 has its own specific class in college. So I had a thermodynamics class. This is way too little of the time for what we are doing right now. One of the assignments that we essentially did was essentially working through various systems and doing what you're proposing right now. Okay, let's change this particular attribute. Does disorder increase? Does disorder increase? And what you will find statistically through all of them is yes. Order, or disorder, right, rather, always increases at a thing. And if order does increase, it is at a sacrifice of disorder somewhere else in the system. Like I said with this right here, okay, can order, if I drop this on the ground, do we expect order to increase or decrease? It naturally, it will, or disorder increases, order decreases. Entropy goes up. Can I put energy in to putting order back to this? 100%. But think about this very carefully. If I put a deck of fully organized cards in here from 2 to ace, all the way through the suits, I put the suits in alphabetical order, and I drop it on the ground, and I randomly put them back together, would you ever expect to get the exact same order out of them? No. Think about how quickly that happens, how quickly I would drop them, how quickly that would occur. And then think about this. Could I then put them back in order? Sure. Am I going to naturally be able to put them back in the exact same order that they came in with as much energy as it took to take them out? Absolutely not. So I can put order back into this system at a sacrifice of decreasing the order of this system over here. So the system as a whole, this order goes up. Questions, concerns? Interesting.
Are we going to be using the entropy,
Oh,
maybe?
no. The main one you'll probably use is delta S equals Q over T.
How would you find W?
The order, I mean, it's just what I said a second ago. It's a probability conversation. So like, what is W? What is W for a coin flip?
I just remember chemistry having a bunch of things with like W be this and this and this.
Yeah, W is the percentage chance that something happens. What is W for a coin flip? 0.5. Correct. What is it for a die roll? 1/6. 0.167, 1666667. Yeah, I mean, for stuff like that, it's relatively easy to see what the percentage chance is, in which case you can calculate that in that particular way. However, for others, it's going to be a lot harder. Yeah. Other quick question. Lillian, did you have a question, comment, concern?
So, like, because you're putting more energy into the system to get it back into that order, right? So does it, like, stay in that system, or is it, like, where does that energy go?
Well, that's the thing. It's always natural processes always create more disorder. Now you start to think about stuff like this. You start to go, well, wait a minute, Spanauer, it gets cold outside. And you said a second ago that cold is bringing about order. So isn't that like basically when cold comes outside, isn't that a bunch of entropy essentially being ordered here? And the answer is yes, but why is it cold? Where is that coming from? And it's from tilting away from the sun. And the sun is weirdly giving us energy, bringing heat, bringing disorder. And it comes to that conversation in the video at the very beginning, that this like energy or whatever it is, we exist in this spot between order and disorder. And apparently there's an exact right spot where we want to be. If I wanted to perfectly order things on Earth, could I make it, or could we as humankind make it that way, make it cold everywhere? Yes, and I think in an inadvertent way we're attempting to do that right now, causing the death of humankind on Earth and making it vastly too cold, and talk about climate change and bring that temperature way, way down. It's going to get super ordered the moment that humans go away, right? We're going to get a lot more ordered and a lot more entropy, but that's going to take, entropy goes somewhere else. It's and I apologize, my conversation here is all over the place because entropy is weirdly all over the place. And honestly, like I said, this topic is way bigger than a half an hour conversation at the end of a lesson. And as such, please keep in mind that when I grade you on this particular section, and I look obviously at your work here, it's probably going to be a similar percentage on the test and the like. And it's a deep conversation. I told you at the beginning of this, we're walking up to the hole that is entropy, and you guys went, holy crap, that's a big conversation. Yes, it is. And if you really want to get into it, it's going to take years and years of work on your part. And some of you want to do that right now, and some of you don't want to do that right now. And the good news is you guys get to choose, because I'm not going to talk about it anymore, unless you guys want to talk about it. That's fine. But other questions about? The real question, of course, that many of you have is how am I going to use this? And essentially, I did that problem very similarly on the board right up there. It's that talking about the Q into a system, the Q out of a system is the same but opposite, right? Q hot. Is Q hot relative to Q cold always going to be negative? What do you think about what Q is? And definitely it is. Meaning, is the hot thing always going to get colder and more orderly? Yes. Is the cold thing always going to gain heat and get less order? Yes, and the temperature is hot is always going to be bigger, and so you do that math every single time. The end number should always be greater than what it started. Disorder in the universe goes up. This is a rough one to hear via video. I apologize.